Okay, so let's continue our march to understanding plane waves and partial waves expansions. We're taking this really incrementally and very fundamentally. We've been working on the time-independent Schrodinger wave equation in spherical coordinates because we're interested in this partial wave expansion of plane waves. Plane waves we understand, right? We've got the e to the I k dot r a plane wave, which we know is not actually a realizable physical state. We discussed this much earlier. So we understand plane waves, and that's basically the time-independent Schrodinger wave equation when you replace the Laplacian with the literal form of the Laplacian in Cartesian coordinates, and this is very easy to solve. When you replace the Laplacian with the spherical coordinate version of the Laplacian, things become quite harder. And we've done 2/3 of the work. Well, I should put it this way. We've done 2/3 of the problem, but less than 2/3 of the work because the radial part is actually the hardest. But we've we've done all the work, right? We've solved the radial equation too, right? And today we're going to focus on this question of the asymptotic form of the radial equation. I'd written this down last time to explain what we were after. And the idea was we know that we have these spherical Hankel functions and spherical Bessel function and spherical Neumann function. I'm just going to call these probably the spherical Bessel functions, plural. This is the first kind and this is the second kind. I'll say Neumann sometimes. I might just call them both Bessel functions, whatever. You know that they're independent solutions of the time-independent Schrodinger wave equation in spherical coordinates of the radial part. And x, we also know, gets replaced with kr, where k is 2 pi over the de Broglie wavelength of the particle, and r is our distance. So in some sense, it's 2 pi times some sort of distance where distance now is measured in units of the de Broglie wavelength, right? We're going to need that in a moment. But the point is what we've discovered is that, well, what we need to discover is that these two expressions have these asymptotic limits, right? And these two expressions for the Hankel functions have these asymptotic limits, which means in the limit of large x, this function literally can be written and replaced with these functions, right? These very simple functions. I mean, look, we worked our butt off to figure out what these things were. And what did we come up with? Well, what we came up with was this. And look at this mess. It's an nth derivative of a cosine x over x times 1 over x. So, holy crap, right? This is 1 over x to the n. D by dx of this thing, you can see this is going to product rule. This is going to be a very complicated expression for any value of n that is interesting. And yet, regardless of how complex this gets, or you could even look at it this way, right? You can look at it, we've got to go to the 1/2 integer ordinary Bessel function and figure out what that thing is. I think I have that here. Right, and look at that thing. That thing is this infinite sum, right? What a mess. So, however, none of this matters because when x is large, all of this stuff, which becomes this thing, ultimately turns into nothing more than the sine of kr with a phase shift. And that phase shift is even pretty simple, right? It's just an integer L times pi over 2. So this is like a pi over 2 shape shift. If L is 1, this sign actually is just, it's just x minus pi over 2, right? If L equals 10, it's x minus 10 pi over 2, which, by the way, is the same as an earlier phase shift, right? Because if L equals 0, these phase shifts are going to start imitating each other. So the asymptotic form of very certain L's is actually going to be the same, right? So this is really, really interesting. And, I think I've got a mistake here, right? Hold on. Yeah, I've got a mistake. Remember, the first Hankel function is the Bessel function of the first kind plus I times the Bessel function of the second kind. And the second Hankel function is just the complex conjugate of that. So if I want to get the Bessel function of the first kind, I have to add these two together, and these two will cancel, but then I have a factor of 2 too many. So what this means is that this guy here needs to be multiplied by 1/2, right? And likewise, this guy here needs to be multiplied by 1/2i. See, so I had that wrong. But regardless, the point is the asymptotes are right. The asymptotes are right. So we want to understand why these asymptotes are what they are. But let's have a quick look at what they are, actually. So remember, I plotted these Bessel functions using Mathematica, right? So here's the Mathematica code. Now what I've done is I've actually, whoops, let me look at a different version of this. Oh, yeah, wait a minute. I changed it. This is the one I want to show you. I changed this, so what I did is I divided x by 2 pi, right? So now, by dividing x by 2 pi, this axis is now in units of the de Broglie wavelength, right? Because x equals kr, which equals 2 pi r over lambda. That's the unit of the de Broglie wavelength. So x over 2 pi is just the de Broglie wavelength. So this is an interesting way of looking at it, because now you can look at these Bessel functions and you can kind of see how, down here, this is 5, 10, 15, 20. This is 5 de Broglie wavelength, right? So the j equals 4 curve has almost nothing going on at the 5 de Broglie wavelength. With the j equals 2, down at the 1 de Broglie wavelength, it's already very, very lax, right, thin. The j equals 1 actually has some substantial amplitude during this process, but these others start rolling over really, really fast. So that's the regular spherical Bessel function. But what I want to show is this function right here. Let's see, which one do I want to show? Let's look at this one. This is J1, right, the first spherical Bessel function. And the blue line is the actual spherical Bessel function, which was calculated exactly. And the dotted line is the asymptotic form of that spherical Bessel function. So what we see is that for the first spherical Bessel function, the asymptotic form is completely bad representation of the function, certainly within below 50 de Broglie wavelengths. But after 50 de Broglie wavelengths, it becomes remarkably tight. At 100 de Broglie wavelengths, it's indistinguishable. And this is obviously the area that is really good. Now, we're going to be dealing with the quantum theory of scattering, right? So our detectors, a de Broglie wavelength for a particle is pretty small. And our detector are many, 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 many de Broglie wavelengths away, much more than 100. So we're definitely operating way out here. And affirmatively, our detectors are functioning are sampling the parts of the radial wave function way beyond where this asymptote is good for J1. For J0, the situation's even better. Look at J0. The two are sort of on top of each other. The two labels are on top of each other because the two functions are literally on top of each other. For J0, it's an absolute perfect match. It's a perfect match. So that's like this asymptotic form and the function itself are identical. Now, why is that? Well, let's go back to J0. Like, if we figured this out, let's just plug into our expression with n equals 0. J0, this guy goes to 0. This differential operator doesn't act at all. So this stuff just goes away. And what are we left with? We're left with sine x over x. Well, what's the asymptotic form for J0? The asymptotic form, if you replace L with 0, is sine of x. L is 0, so that term goes away. So it's sine x over x. So in the case of J0, the asymptotic form actually is the function itself. Ergo, this function is a perfect match. However, that's not true for the first function, for J1. It's not true for J1. Now, I have some other examples in here. First, if you need any convincing, here's J1 again. And this should be A1, right? This should be A1 is the A1, this represents the dotted line, which is the asymptotic form. And again, this I just plotted out farther, just so you could start seeing that, look, out here, the dotted line is running right over the blue line, right? So that's for the first Bessel function. Now let's look at the Neumann function, right? For the Neumann function, here I've plotted the first Neumann function in blue, and then in dotted black is the asymptotic form. So this is, and it has sort of the same issue, right? It's not so accurate early on, although I got to say it's could be worse. Although it's 0.1 versus 0, that's pretty substantially off. Interestingly, the phase isn't terrible, but the phase starts locking on right there at around 80, 100, 120. It's pretty locked on, and so there's clearly this is going to get pretty accurate above 100 de Broglie wavelengths. And this is for Neumann 10, right? Neumann 10. And here we see, okay, things start to get be a bit of a mess, right? Now, for the Neumann 10, the phase shift is huge. It's like 90 degrees. It can't be any wronger. Can't be any more wrong down here at 100 de Broglie wavelengths. The amplitude's not so bad, but the phase shift is bad. And if you look at it, if I blow it up, here I blew it up between 320 and 380, and you can see how bad Neumann 10 is in that range. However, for Neumann 10, I plotted it way out there, and at about 1,000 pi, well, I guess that's about 3,200 de Broglie wavelengths. By the time you get 3,200 de Broglie wavelength, it's locked on again. So these guys do get locked on. They get locked on later and later, the higher the order. But the most important orders that we deal with in scattering theory are the lower ones, right? So we're dealing with Neumann 1 and Bessel 1. Anyway, the point is that all that matters to us as a matter of practicality is just these forms. And since the theory is so dependent on that, we're going to spend some time today in understanding how do we derive these forms if we know these forms. And this is a bit of weird math, and the rest of the talk is about it. If you're satisfied with this, then you're done, right? Quantum mechanics textbooks don't go into what we're about to talk about. So as long as you can now translate in your mind from here to here, despite the fact that these guys don't solve the appropriate differential equations, but in the asymptotic limit, when x is large, they do. If you can get your head around that and you're comfortable with it and you feel ownership of this, then you're good. The problem is I never did, right? I really kind of did have to figure out this whole thing. I just had to, and I'm not, that doesn't mean, it's actually a little obsessive compulsive. It's not, part of navigating through the education of physics is figuring out how deep down each rabbit hole you want to go. Right? It's really like that. And the guys that go down all the way through every single rabbit hole, right? That's not necessarily the guys who come out on the other side of this in good shape, right? Sometimes they get lost down there and they just get frustrated and they never emerge. At some point, you have to just sort of put things on a shelf and say, okay, this is the asymptotic limit. I went to Mathematica. I proved it for myself. I feel comfortable with it. No, I don't know how it was derived, but I'm smart enough to know someday I can figure it out if I need to. That's fine. That's a fine way to go. The rest of today's lecture is figuring out how this came about. And even that is, I'm going to do it quickly, right? And there's still going to be rabbit holes. Anyway, let's begin. All right, so what we're after is a review of the topic called asymptotic methods. Asymptotic methods is a particular branch of mathematics. You can take classes in it. Whole books have been written about it. I have a couple. And it's basically a black art. It's one of those things that were done in the 19th century a lot, and everybody who does practical physics needs to understand this stuff really well. It blends really nicely into perturbation theories. But it's hard stuff. I think it is, personally, I think it's hard stuff. It all revolves around the topic of complex analysis. And this is why I really feel it's important to put this in our QED prerequisites. People who enter QED without a solid foundation, comfortably working with certain types of elementary complex analysis. It's funny, you don't need a lot. A one-semester course in complex analysis actually covers more than you need, right? If all you know is these core concepts, then you can advance. But those core concepts are really important. In fact, my QED book that I recommend people, which is Peskin and Schroeder, right? The introductory chapter, the first chapter that explains why QED is so important, kaboom, complex analysis. It's got contour integrals, it's got branch cuts. I don't think it uses the residue theorem in the first chapter, but right away you're in the middle of a complex analysis discussion, and it's an important one. So that's why I feel it's okay to spend a lot of time on just this one point, because we're going to ultimately get to the method of steepest descent, which is all about complex analysis. Well, it's steeped in complex analysis, but we're going to get there through Laplace's method first, which is all real, the method of stationary phase, which is our first step into complex analysis, and then you combine these two together and you end up with the method of steepest descent. That's sort of the strategy that I plan to do here. It's not a unique strategy, by the way. It's how I learned it, and it works really well. So with that in mind, let's begin. So we begin with Laplace's method, and I will point out a few things. The most important thing, of course, is what does Laplace's method give us? And it gives us the asymptotic form of a function. But what kind of function? Well, it has to be a function that is described by an integral representation of the form as depicted right here. It's a definite integral, and the variable of integration is t, which is a real variable, and then you have a function f of t and another function psi of t. Psi of t lives in the argument of an exponential along with our variable x. X is the dependent variable of our function. Notice that our dependent variable lives in an integral representation in the exponent in the exponential. And it's all by itself. It's multiplied by a function of t and then exponentiated and then multiplied by another function of t. So this is kind of a specific type of function. And that means that I has an integral representation. And an integral representation is really important and very, very common. When you study special functions like the Bessel function or the spherical Bessel function or Legendre functions, if you really get into it, you learn a lot of different integral representations for those functions. And it's funny because you almost never see them applied in physics too much. But today we are going to actually, well, not today, but in these following lessons, we're going to discover them and apply them. And we're going to apply them because they are what we use to get asymptotic forms. So with this in mind, we now know that Laplace's method is when we have a function of a real variable and a real integral representation for that variable. And we're looking for the asymptotic form of this for x is much larger than 0. So let's see how this might work. So the basic idea here is going to be that the value of this integral is really going to be dominated by the portion of the integral right around t sub m, where t sub m is the maximum value of this function psi, the function that's in the argument of the exponent or in the exponential. Wherever t sub m is, it's going to turn out that for large values of x, the entire integral on the interval a to b, that entire definite integral can really be just cut down to just this little part, plus and minus epsilon around this one key point, this one point of maximum of this function psi. And in fact, all of these methods that we're going to study and the ones that give us the answers we're looking for the Bessel function, the spherical Bessel functions, are based on that principle that we're going to have an integral representation that's going to have some sort of exponential piece. And by studying the behavior of the exponential, we're going to learn that only certain pieces of these integrals contribute significantly. Then we're going to focus on those pieces, simplify the integral, and that'll be our asymptotic solution. Now, it turns out in this case of the real, where everything's real, the part of this exponential that matters is the part right around t equals t sub m, where phi of t is a maximum. So let's understand why that is. So consider this graph of phi of t, where there is a maximum, and the boundaries of our integral between a and b. So phi of t definitely has a maximum. Now this maximum is only, it's bigger than it's bigger than every point. It's the maximum, but it's not hugely bigger. It's hard to believe that if you just drop this down to t max, that our integral would only depend right around here, right? Depend on the integral right around t max and not here or here. It's not like those are zero, right? There's substantial amounts of phi of t, right, above the axis, the way I've drawn it in this example. But the first thing, of course, to remember, is that we're dealing with e to the x phi of t, right? So the function itself is being multiplied, and of course there's f of t here, right? So the integrand actually involves the exponential of this graph, right? So once you exponentiate this, the large parts are going to be popped up even more, and the lower parts are going to be suppressed relative to the large parts by an exponential factor. And in fact, that really drives the whole narrative here, because what's going to end up happening is if you just plotted this, it would tend to look something a little bit more like perhaps even like this, right? Let's just say, right? It's very imprecise. But the point is that all of a sudden you do see the sense that this exponential, just by virtue of this maximum, is going to peak out a lot more than you might expect. But then you add in this x. And as x gets large, this behavior of peaking gets even more and more dramatic, right? So there is reason to say that Laplace had a pretty good idea here. So let's now imagine that we zero in on this peak point. And the peak point we know is such that phi of the peak point is a max, right? And we know that phi prime at the peak point equals 0. And we know that phi double prime at the peak point is less than 0, right? Because the slope is the slope is decreasing, right? Slope is high, 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 0, negative, negative, negative. So the slope must be less than 0. So we now can replace the function phi by its Taylor series right around this maximum point. And if we did that and only did it to two terms, we would get a parabolic representation of the function at the point. And here I've kind of drawn some parabola. It's probably not a good representation of this particular circumstance, but it's close enough, right? So this parabola is our second order Taylor series representation of psi around this point. And what we're going to do is we're just going to put that second order representation straight into the integral, and we're going to see what that gets us. So we go back to the integral. Here's our integral, and we put in this Taylor series, right? We ignore the higher order terms. The first order term is 0 because we're dealing with a maximum. Tm is a maximum. And you'll notice that the variable of integration t only appears here to the second power. And so our integral now becomes this thing right here. And what we see is we evaluate we're now going to evaluate f at the maximum, and we're going to take e and raise it to the power of that Taylor series. So you'll see our independent variable x is now appearing in each term. And this is going to be the integral we are going to focus on. And what we're going to say now is that I can pull out these two terms, the f of tm and the e to the x phi of tm. Those are no longer functions of the variable of integration. And then I'm left with this integral. It's basically Gaussian, right? Because if you look closely, this is a constant. The second derivative at the point of maximum is a constant. X is a constant relative to the variable of integration. The only thing that's not a constant is t minus tm squared. So this is actually a Gaussian integrand, right? Because everything in here is in the exponent. It doesn't look like that. The LaTeX doesn't do a good job to do that. I should have written it as this, exp. I should have written it this way, right here. Right, so then you would be no doubt that everything there is in the integrand. Okay, but with this, we can now just do a change of variable to make it look literally like a Gaussian. But we know a few things. One is we know that given that we're working at a maximum point, we know that the second derivative is going to be less than 0, right? It's going to be negative. So I can replace that second derivative with its absolute value and then throw in a negative sign, right? So that's totally fair. And when I do that, I can make a variable substitution where I can call this u, t minus tm I can call u, and then I can change the integral to this form right here, which is literally a Gaussian now. It's a Gaussian in the more classic form, centered at 0, where u equals 0. And so this boundary of integration is actually now got to change. And what does it change to? It changes to minus epsilon to plus epsilon, because I've changed the variable to u, right? So with that in mind, let me get rid of those guys. And with that in mind, now I'm looking at a Gaussian integral. Now I'm claiming that our integral is approximated by this over a very, very small range of epsilon. Now look, the fact is that's got to be the case, because if it isn't, I just choose x to be big enough so that it is, right? Now this Gaussian literally looks like this with a height, right? Let's just call that Gaussian. It has a height of 1, right? There's no prefactor for the integrand, right? Obviously, this is a prefactor here, but let's ignore that for a moment. And let's just go with the sort of the standard Gaussian. It's got a height of 1, and it's got a width, right? The width is going to be 1 over the square root of phi double prime over 2, right? The square root of phi double prime over 2 x, right? So everything is in the square root there, right? There, my little meter. That's going to represent the 1 over e height of this Gaussian, right? The Gaussian will have decreased to 1 over e when u takes this value, right? So the point is that the bigger x is, the narrower this Gaussian becomes, right? And eventually, if I can make this Gaussian as narrow as I want, right? And it gets narrower and narrower just the bigger I make x. So the point is that for large x, this really is picking out this value out of the integrand, right? So this whole definite integral, the contribution away from it is really, really small, right? So I can really say that I'm dealing with some small interval around a 0 in the case of u, right? or around the maximum in the case of t, right? Which is just one small change of variable away. But the point is after I've decided that I've got a narrow enough Gaussian, you know what I say is I don't need to worry about epsilon, minus epsilon, and plus epsilon, because the stuff in the tails here, the stuff beyond epsilon, is so darn small that it's called transcendentally small. It's so tiny that it doesn't even matter. So you know what I'm going to do? I'm going to say, to heck with those epsilons. I'm just going to integrate the whole thing to positive and negative infinity. Right? Forget it. I know that x is big enough that if I add in those tails, it's not going to pick out anything else. Remember, you're multiplying by another function, f, right? So there's another function out there, f of t. And what I'm worried about is contributions of this number multiplied by that number, right? It's the integral is f of t times this exponential. So if I'm worried about that product, out here, that product is totally zero, right? And it becomes something non-zero really right in here, and then out here it becomes zero again. But it's zero, so I can go ahead and extend these integrals out forever because this Gaussian is going to kill everything. Now, there are some conditions on f of t and psi of t. We're not going to worry about them right now. We're just using it for functions that are well enough behaved that all of this stuff makes sense. So I now create this integration, right? I've got this thing up here. I'm basically saying, well, I remember this is just plus e and minus e. Once you're in the u, right, you don't have to have these TMs there. But now I have this full integration on the whole real line of a Gaussian. And this integral I know, right? Because I've studied enough math to remember that minus infinity to infinity of e to the minus x squared dx equals the square root of pi. And I know, because I know basic calculus, that if I put an a there, that's going to end up making it square root of pi over a. So being able to execute this integral where a is now going to be all of this stuff, right? And I now just make that substitution, right? And I end up with this part here, pops right down there, and then this integral gets churned through this standard form, which presumably right? If you don't know the standard form, this is a rabbit hole worth going down, right? If you don't know the full value of the Gaussian integral equaling the square root of pi, it's kind of a fascinating thing. It's a definite integral of an exponential equaling the square root of pi. It's kind of fun. You should know how to do that integral. Meaning you shouldn't know necessarily how to from scratch do it if you've never seen it. You should be able to go and follow the derivation of this integral very well. It's just some clever calculus, right? But knowing this standard integral, you can now take this for a, throw it in the denominator. So the pi's up there, the 2 goes into the numerator, the second derivative goes into the denominator, and x pops out as x to the minus 1/2, right? And there you have it. This is literally a formula now, right? This is a formula that kind of tells you the answer for any object or any function that has this kind of integral representation. So Laplace's method isn't something you necessarily have to apply from soup to nuts each time. If you learn the formula well enough, you can do it. But this would be one of those formulas that it would be a rabbit hole formula. You would look at it and you would say, sure, I can understand this, but I don't know where it came from, and therefore I don't feel ownership of it, so I just have to run it down. And that's what we just did, okay? So we just ran down Laplace's method in its most simple incarnation. So the next method we need to understand is the method of stationary phase. Now the method of stationary phase, look, wow, same type of integral. Look at that. Except now you're dealing with a complex exponential, right? It's still a function of a real variable t, but the exponential has that I in it, right? So by Euler's expansion, you can immediately can think of it this way as an exponential to a real part plus a complex part. But the point is, it's a different kind of integral altogether. It's not, it's a complex, it's an integral that leaves you with a complex valued function. I is essentially a complex valued function because you're never going to integrate this I away. X is still a parameter, just like before, so x is the argument of our function, but as far as the integral is concerned, x is a constant, and the constant of integration is t. Oops, wait a minute. Look, I did this wrong, right? E to the I x 5t. This exponential goes away if you use Euler's rule, right? So if you use Euler's thing, this thing goes away, right? And so what are you left with? You're left with f of t times the cosine of and I times the sine dt. And the reason I wanted to do that is you want to see that f of t is being multiplied by this function. You can break the integral up into two parts, for example. And f of t in the first part is multiplied by cosine, which is oscillating. This is an oscillating function. It goes from +1 to -1, +1 to -1. And it does so at a frequency driven by its argument, right? T is the dependent variable, right? So t changes. So if phi of t is large, then the frequency of oscillation is going to be fast. As t moves a little bit, if phi of t is large, this is going to be a fast oscillation. And if x is large, right, this is going to be, in particular, if x is large, then even if phi of t is kind of middling, this is still going to be oscillating quickly with respect to t. It's hard to judge how quickly cosine will be oscillating. The point is if phi changes at all substantially with t, then this is going to oscillate quickly. Likewise with sine. And the point is anything that oscillates quickly from +1 to -1, +1 to -1, it's going to tend to do if this is f of t and our cosine of t term is doing this, right? If it's oscillating a lot faster than f of t is changing, these pieces are all going to cancel each other out, right? And so this kind of interval could be really, really, really small, or it would be extremely sensitive to the bounds, right? The bounds of the definite integration. That should be a definite integral, by the way. So the point is we need to find places where phi of t actually is stationary, right? Is stationary, meaning it's relative to t, phi of t is not changing much, right? Now, that would be at a maximum point or a minimum point, right? It could be either of those, right? Anywhere where the first derivative is 0 is going to give us one of those stationary points. But it's for a different reason. It's not because it's a maximum and it picks out a particular part of the integral like we had before. It's actually because what ends up happening is these oscillations, when phi of t has a stationary point, these oscillations tend to kind of slow down. And in that area where phi of t is stationary, or phi prime of t is 0, this section of the integral will in fact contribute, while the rest of the stuff kind of cancels out. So we're still looking for extremal points of phi of t, but for a totally different reason. And that's what's really important here. Now, on top of that, if x is large, right, if x is large, phi of t is going to have to be very, very steady if x is large for this contribution. In fact, it's again a situation where x being large makes the situation for this oscillation part even worse, and it makes the situation for the stationary part even better. So with that in mind, let's look at the same process we just did, right? We did what we did before. We're going to do the same thing. We're going to find and substitute the Taylor expansion. We look for a place where phi prime is 0, and that Taylor expansion gets us to the same place, right? But now we have a different integral. This is not a Gaussian integral. It kind of looks like it, right? You got the u squared, right? You've got something that looks like it could be a, right? You have all of this, which could be a, but you've got this I, and that screws the whole thing up, right? Once you have the I there, you no longer have a true Gaussian integral. But you still have an integral that we know the answer to, right? We know this. Now, I got to admit, this one I don't have memorized, right? This one I don't know. But this one is, it's basically a version of what we call Fresnel integrals, and it is well known. But look at this weird result, right? It's the same result as you would have had for a Gaussian, which is pi over a, because it is almost a Gaussian. If not for that I, right, this would be a Gaussian. So you do get this Gaussian effect, this pi over alpha. This isn't an a, this is an alpha, isn't it? But you end up with this e to the I pi over 2. And actually, that's not right. It's e to the I pi over 4. It's e to the I pi over 4. E to the I pi over 4, that's kind of an interesting number, right? If you plotted it in the complex plane, it would be something like, it's on the unit circle, as all things e to the I are, but it's like right here. It's not I and it's not 1. It's square root of 2 plus I square root of 2, right? So you've got this neat thing, this phase shift. This I sort of adds this phase shift to what would have been a pure real number. But with that, I can now make the substitution for this integral, right? Up to here, this is exactly the same math we used to get to here, right? In the Laplace method. The only difference now is this I kind of followed us around, and it killed our opportunity to use the straight up Gaussian integral that ended up with pi over, alpha. What it does is we have to learn a different Gaussian interval, and it introduces this pi over 4 piece. So you end up with this expression here. Same expression, right? It's the same expression. The difference now is that this constant term that pops out is, or a constant in terms of the integral, right? Meaning this guy that pops out of the integral now has a leading I in front of it, right? So that's some unit circle imaginary number, and before it was just real. And you have this I in here, like I said. So that's this part, and now this integral contributes an additional phase of plus or minus I over 4, and we'll see which one it is in a moment. And then you have the same square root over the second derivative, and you have the same root of x, 1 over a reciprocal root of x behavior. So this asymptotic property is actually very, very similar, but when you crunch it, it's substantially different because of this phase shift and this complex piece. And let's see, why is there a minus sign here? The minus sign is because this stationary point, it could be, for the stationary point for the function phi, it could be a maximum or it could be a minimum. So this second derivative now could be plus or minus. And if it's minus, then then alpha becomes negative. And if alpha is negative, then you end up with, you could get a magnitude of alpha, and then I think you end up with a minus I out in front. But minus I is e to the minus I pi over 2. And then you multiply that by e to the I pi over 4, and you get e to the minus I pi over 4. And that would be the minus sign. So the plus or minus really depends on whether or not this second derivative is positive, the second derivative here is positive or negative. So that is the method of stationary phase. Okay, so the next method is the method of steepest descent, and we will do that in the next lesson.